All right, thank you, Professor Misbahi. And thank you, everyone, for taking the time to attend today. So my name is Christopher Lum, and today I would like to brief you guys a little bit about our JCATI-sponsored work, which is concerning creating a collision warning and awareness system for multiple aerial entities. And I just want to take a minute to also acknowledge my co-PI on this, Dr. Joris Wagner, also at the University of Washington. Actually, maybe I'll take this off so we can kind of talk maybe easier. But Joris and I at the UW run the Autonomous Flight Systems Laboratory. So the goal of the Autonomous Flight Systems Laboratory is really to conduct research which advances technologies which are relevant to unmanned systems. So historically, the majority of our work has been focused on control algorithm development, but we're also very interested in things like flight testing and integration, human-in-the-loop architectures, and really general UAS research in general. One of the things I think that makes our group unique is that we are very interested and focused on transitioning ideas out of an academic university environment and onto fielded systems. So what this current JCATI project focuses on is partnering with Insitu, which is a UAV company that actually Dr. McGeer started, and they're based out of Bingen, Washington. They're actually a wholly owned subsidiary of Boeing at this point. What they've done historically is produce the ScanEagle UAV, and you guys have probably seen footage generated by the ScanEagle. You guys may have recalled the 2009 hijacking of the Maersk, Alabama. Well, that footage was provided by a ScanEagle. So as Insitu is starting to diversify their product line, one of the newest and most exciting pieces of technology that's coming out of that company is not actually another aircraft, but rather it's a ground control system and software package. The system is called the Insitu Common Open Mission Management Command and Control, or ICOMC2 system. The idea with ICOMC2 is that it's a software package that's going to allow an operator to interact with the ground station in a nice, easy-to-use fashion. This system, in turn, is going to be able to communicate and control one or multiple STANAG 4586 compliant aircraft. Now, what makes ICOMC2 so unique is that it supports a fully documented software development kit that can be used to expand the core functionality of the system. So our JCATI project actually makes extensive use of this fact because what we're trying to do is create an additional application which runs on top of the core to extend the functionality of the entire system. Now, this software model probably sounds familiar to you, and personally, I think about it every single time I download an app onto my phone, right? It's effectively, I know Insitu probably doesn't want me saying this, and this is probably not in their official marketing term for the system, but I kind of like to think of ICOMC2 as almost like an app store for UAS, right? Do you guys remember all those iPhone commercials from a couple of years ago where they had all this happy background music, and they're like, oh, do you want to check how many calories were in your lunch? Well, there's an app for that. Do you want to log into your webcam so you can watch your dog sleep while you're at work? Well, there's an app for that, right? In our situation, what we want to do is take the system and extend the core functionality to assist unmanned systems. So our system might be more like, do you want to increase operator situational awareness in a multi-UAV stochastic system? Well, we have an app for that, right? And I guess if you say it like that, it doesn't really roll off the tongue, so I'm sure Insitu's marketing team needs to do a little bit of work on that before we actually run the ad, but that's the general gist, right? So what are we trying to do here? There's been a lot of talk here, and I'm sure I've been chatting with people at the networking session. There's a lot of excitement about the possibility of operating multiple aircraft simultaneously in the national airspace in the near future, right? Amazon.com would love to have you believe that in the near future we're going to have a swarm of drones over the city dropping packages off to you within minutes of purchasing it, right? But the reality is, in order to get that kind of vision to become a reality, there's a couple of infrastructure and baseline technologies that I think are important that we need to investigate. And collision avoidance is probably one of the most important of these. So what do we have to worry about with collision avoidance for unmanned air systems, right? So the FAA and the media would probably like you to believe that you really need to worry about collisions with between unmanned systems and general aviation traffic, right? This actually has occurred, right? So this is a couple of pictures here showing an incident in 2011 where a C-130 actually collided with an RQ-7 Shadow over Afghanistan here. I don't have a picture of the RQ-7 because, as you can probably imagine, it didn't fare too well in this meetup. I thought it was kind of interesting that Bill Rodman was talking about, they worked on wings for the RQ-7. So, maybe if he had his wings on this, the shadow might have turned out a little better. But in this case, it didn't work out so well. What else do we have to worry about? Well, in addition to mid-air collisions with other general aviation traffic, operators are actually very concerned about conflicts with airspaces as well. They actually spend an inordinate amount of their time monitoring flight paths to make sure that they don't intersect with no-fly zones. And you might think this is trivial, but I mean, it does make a difference. If you Google for no-fly zone, this is one of the first images you get. And as you can probably imagine, this is sort of a big deal to make sure you don't intrude on no-fly zones or go where you're not supposed to. So in any case, what really causes a problem from an operator's perspective is really a lack of situational awareness. So what we are trying to do is basically to create a collision warning plugin or app for the ICOMC2 system, which is in charge of increasing the operator's situational awareness with respect to future collisions or conflicts. So how are we going to do this? Well, because the goal of this technology is to get it in the hands of Washington Aerospace where it can help operators, we actually went down to our industry partner Insitu and we did a couple of interviews and focus groups with various aviation industry experts and asked them, well, how would this be useful to you? So I think one of the easiest ways to look at this is maybe let's just walk through a use case of how this system might be used within ICOMC2. So in this scenario, you might have multiple entities in your theater of operations. What we'd like to do is provide the operator some way to select from that list and say, there are certain aircraft that you care about our plug-in managing. Once the operator has chosen these entities for the plug-in, they would be able to select an individual vehicle and then potentially modify vehicle-specific parameters. For example, they might increase the buffer radius or the airspace that a certain vehicle claims. Once the system has all of this information, it would be able to run some kind of stochastic analysis and provide feedback to the operator and highlight areas of potential collisions or conflicts in the future. So behind the scenes, though, what we're doing is we're modeling these aircraft as point masses with 3D kinematics and cylindrical airspaces. We also want to model the positions of these aircraft as stochastic random variables. So we use a two-dimensional Gaussian distribution to describe the planar position of the aircraft with an independent normal to describe the altitude here. Once we've got all of that information, we can now propagate the system states forward using a stochastic error propagation technique. So for example, on the graphic you see on the right, if the aircraft starts out there in the background, we're able to propagate the system states forward and estimate where it's going to be. And you can see that it's illustrated by the fact that you've got these increasingly large confidence ellipses as you go forward. So finally, once we have these future state estimates, we're able to convolve these and integrate them together to provide conservative probabilistic estimates of potential future conflicts. So I think the easiest way to look at this is maybe to just look at this scenario in action here. So we've got a very simple simulation showing how this system works. So to briefly describe it here, we've got two entities here. We've got one aircraft off to the west, which is supposed to simulate a commercial airline flight going from Seattle to Pullman. Maybe this is the flight some of you guys were on. Personally, the students and I, we actually caught the bus. And actually, there's a funny story with the bus, too. So we picked up the bus at UW and came over here. We were expecting it to be like this Greyhound charter bus, but when we picked it up, it turns out that somehow it was actually the University of Washington football bus. So it's this big purple and gold monstrosity that they drove over here and parked behind Cougar Stadium. So I think the driver said she was going to stay with the bus because she was a little bit nervous about leaving that bus on this campus unattended, but I don't know. But anyway, we've got that commercial airliner, which is just heading east. And then we've got a UAV, which is launched from the UW campus, actually Drumheller Fountain there. And it's just going to follow this flight path, which is illustrated by that cyan-colored line. So let's just take a look at the scenario and just let it play out and see what happens. So as we let this thing go, you're going to see that the airliner just continues eastward. And the UAV is following this upward spiral to gain altitude before it heads off north on its flight path. And you see, due to extreme unfortunate, or actually engineering in our scenario, near the end of the simulation, they come pretty darn close to each other. They don't actually collide, but we consider that a conflict. So let's restart this simulation and turn on the collision awareness system and see how it helps. So we're looking at this from the UAV's point of view. So you see that down there, in that blue cylinder represents the aircraft's airspace. It's colored blue because we say blue is nice, there's no chance of collision right now. We can pause the system and look at why is there no chance of collision. Well, the system is actually propagating or scanning forward in time along the intended flight path and propagating the states forward using this error propagation method. And we see that, well, there's no estimated future collision because these estimated future states don't intersect with the airliner's future states. So the aircraft just goes ahead and continues on its mission here. So as we go forward, I want you to pay close attention to the cylinder here. You're going to see that as we get closer to that conflict area, the system begins to warn the operator that you have a potential impending collision in the future. It does this by highlighting where the collision may occur, and we go from blue to red to kind of show you have an increasing confidence, or you need to start worrying about this scenario here, right? So you see that if the operator ignores those warnings here, we're actually plotting now the scan eagle's airspace in this red cylinder here. You'll see that near the end here, that airliner does actually breach your airspace, and we get this conflict as predicted. So that's a pretty simple scenario here. We've looked at more complicated test cases as well, but I thought this was the best way to kind of illustrate at a high level what this system is doing currently. So that was the technical side of our project here, but as you all know, JCATI has an educational mission statement as well. So I just wanted to take a couple of minutes to talk a little bit about some of the educational benefits of the JCATI program at the University of Washington. So over the past 10 months, our group has been very fortunate, and we've involved approximately 20 undergrads, 2 graduates, and 2 alumni students, one of which you'll actually be hearing in the immediately following panel here. All of these students have been able to gain exposure to relevant STEM fields such as software engineering, autonomous systems, verification and validation, et cetera, right? This research project has also produced over 133 research credits, and by the time we're done, we expect 2 master's theses to be produced out of this. What we're most proud of, though, is that out of these students that are involved with our JCATI project, 6 of them have been placed into industry as a direct result of being involved with this program here. So 2 of our students have accepted full-time positions here, one in California, and actually both in California, one with Boeing and one with a space systems company. 4 of them have been awarded internships for this upcoming summer. Many of these internships are with our industry partner Insitu, and 2 of them have actually been motivated to pursue grad school to continue their studies in autonomous systems. So as this project kind of wraps up to a close here within the next 2 months, we're starting to look at what future endeavors might our group be able to pursue thanks to this JCATI project and the technology that's been produced from it. So right now what we're in the midst of doing is transitioning some of this technology to our industry partner. We're hoping to work with our university's commercialization office and get this system over to Insitu and entering service within the next year or so. Our group is also very interested in potentially using the technology and research developed during this project as a springboard to apply for other opportunities. For example, we're currently pursuing additional JCATI funding for other works related to unmanned aerial systems. There's also a National Science Foundation solicitation for cyber physical systems, and DARPA is about to issue an RFP for collaborative operations of UAVs in denied environments. And perhaps the most interesting of all of these future opportunities is the FAA is about to release a solicitation for an upcoming Center of Excellence, which is focused on unmanned aerial systems here. And 2 of the specified research areas of this upcoming Center of Excellence are both communication/control and also detect and avoid. So a lot of the technologies and research done during this project is going to enable the University of Washington to be an excellent contender to fulfill those 2 roles right now. So just in closing, I hope this short briefing has illustrated how this JCATI project has allowed us to provide engineering, aerospace-related research and employment opportunities for students at the University of Washington, and also to pursue joint industry-university research in new technologies, which we hope are very relevant to the future of the Washington aerospace industry. I just want to take a quick moment once again to acknowledge and thank our industry partner Insitu for all of the support they provided during this project. And first and foremost, thank the Joint Center for Aerospace Technology Innovation for supporting all of our research and our students over this 10-month period. And with that, I guess I would be happy to take questions. Yes, Professor Shen?
So, Chris, I was asked to repeat the question.
Yes. Okay, so Professor Shen's question was, how many seconds does the operator have to react before taking action here? So that's programmable right now. It's a sliding window. That current simulation you just saw was only 10 seconds. And as you can probably imagine, unless you are a stick and rudder fighter pilot, 10 seconds is not enough. Interestingly, so Art Crow here is actually a fighter pilot. And we talked with him a little bit about trying to ask how much time does an operator need here. So, you know, a traditional stick and rudder pilot who was in the seat, 10 seconds would be enough. But since these are remote systems, the time scales are much longer. So when we've been talking with Insitu operators, they've said anywhere on the order of 1 to 2 minutes may be reasonable. So if you get a warning that you may have a problem in 60 seconds, you might have enough time to react at that point. So we're looking at around maybe 60 to 120 seconds as a first cut. Yes, Dr. McGeer.
Avoiding mid-air collisions and about the interest that people have in sense and avoid. The impression can be created that mid-air collision is actually a significant risk. And as you know from your own analysis of this problem, it isn't. So I encourage you to make a few comments on that.
Yes, so that's a very good point. So what Dr. McGeer was alluding to here is that there is significant political and other momentum here directed towards this concept of sense and avoid, whereas there is a lot of actual research done by various groups, both at the UW and other locations, to suggest that really mid-air collisions are not your main concern. And that's absolutely true from a lot of the analysis that several, like our group, Dr. McGeer's group, several others have looked at. What you really need to worry about in some of these scenarios is not necessarily mid-air collisions, but strikes to innocent bystanders on the ground due to potentially just general failures. If your engine conks out here, your aircraft is going to come down and potentially strike bystanders on the ground. And that actually, from a probabilistic, I mean, to be slightly macabre, if you're talking about how many people do you expect to kill per flight hour, the number you expect to kill on the ground is much more than you expect to kill in the air. So mid-air collisions are likely not the scenario you need to worry about. That's why we were actually focusing a lot on these collisions with airspaces, because that is something operators tend to worry about. We did throw in the mid-air collision because, like you mentioned, there's significant desire to see that issue addressed, regardless if it's engineeringly sound or not.
Research, and let's thank Dr. Lam again.
Thank you.